Dinosaurs dominated Earth for 165 million years. They survived volcanic eruptions, climate shifts, and multiple extinction events. But 66 million years ago, in a single day, everything changed. A gigantic asteroid slammed into Earth. Within hours, the skies turned dark. Wildfires spread across continents. Ecosystems collapsed, and approximately 75% of all life on Earth was pushed toward extinction. What did the dinosaurs experience during those final hours? This is the story of the last day of the dinosaurs, a few terrifying hours that forever changed the history of life on Earth. Millions of years before life on Earth reached its peak of diversity, when dense forests blanketed the continents and dinosaurs ruled every ecosystem. A quiet chain of events had already begun in a distant corner of the solar system. It started with nothing more dramatic than slow collisions between ancient rocks drifting through the cold expanse of the asteroid belt. This region of space contains millions of remnants left over from the formation of the planet some 4.6 billion years ago. Most of these bodies follow stable orbits. But at times, the gravitational pull of giant planets, such as Jupiter, can alter the path of certain asteroids. A slight disturbance, a subtle gravitational tug sustained over millions of years, is enough to transform a harmless rock into a fateful traveler heading toward the Sun and ultimately toward Earth. A minor collision in deep space can trigger a chain reaction unfolding across millions of years. That is the nature of solar system dynamics. Every motion is interconnected. And sometimes the smallest changes lead to consequences on a planetary scale. The asteroid responsible for the catastrophe at the end of the Cretaceous period is believed to have been a fragment formed from ancient collisions between silicate-rich and metallic asteroids. Yet its orbit was gradually shifting, little by little, under the gravitational influence of neighboring planets. Dynamical models suggest that large asteroids may require tens of millions of years to transition from stable orbits into paths that intersect Earth's orbit. The contrast forms one of the greatest paradoxes in the history of life. While ecosystems flourished in stability and abundance, a cold and inevitable physical process was quietly advancing beyond the atmosphere. How many times in planetary history has the course of evolution been shaped by wandering stones in space? We will follow that final journey as the asteroid approaches Earth. And everything changes within a matter of minutes. The moment began with a streak of light appearing along the edge of the ancient sky. A celestial body roughly 10-12 kilometers in diameter racing toward Earth at nearly 20 kilometers per second. equivalent to about 70,000 kilometers per hour, faster than any natural object humanity has witnessed in modern history. At that speed, the asteroid did not simply fall. It slammed into the atmosphere like a colossal bullet, carrying unimaginable kinetic energy. The violent compression of air in front of it generated a blazing plasma sheath that enveloped the body. A massive fireball brighter than the sun when seen from the ground. As the asteroid plunged downward, a shockwave formed ahead of it, like an immense wall of compressed air forcing everything aside. Its sound, if anyone had been close enough to hear it, would have resembled unending thunder, powerful enough to shake the ground even before impact. Atmospheric friction did little to slow it due to its enormous size. Instead, the outer layers of the asteroid began to melt and vaporize, leaving a luminous trail stretching hundreds of kilometers across the sky. The impact site lay in what is now the Yucatan Peninsula, then a shallow sea rich in carbonate and sulfur-bearing sediments. That location played a critical role in the scale of devastation that followed. Because when sulfur-rich rocks were heated, they released vast quantities of gas into the atmosphere, amplifying global climate effects. Viewed from space, the scene would have resembled a brilliant spark piercing through cloud layers, leaving behind a long plume of plasma. But from the ground, it would have looked like the end of the world approaching. Blinding light, rapidly rising heat, and air trembling violently. What followed was no longer a single collision, but a chain reaction on a planetary scale. Rock vaporized, shockwaves rippled around the globe, and a colossal impact crater began to form. Next, we will witness the moment that altered history, when the energy of the impact unleashed one of the largest explosions ever to occur on Earth, and set in motion a cascade of global catastrophe. In less than a single second, the entire store of kinetic energy accumulated over millions of years of motion was unleashed, equivalent to more than 100 million megatons of TNT, billions of times more powerful than the atomic bomb humanity has ever detonated. At the point of impact, Earth's crust was forced downward and then rebounded like the surface of water struck by a massive object. Pressure surged to hundreds of gigapascals, and temperatures soared to tens of thousands of degrees Celsius, hot enough to vaporize rock almost instantly. A colossal crater began to form in the region now known as the Chicxulub crater. a complex structure featuring a central ring of mountains, compressed rock layers, and fractures radiating thousands of kilometers outward. Within the first few minutes, vaporized rock and sediment formed an immense column of material blasted high into the atmosphere and even beyond near-Earth space. This ejecta included molten rock, water vapor, and sulfur gases, creating a superheated cloud that spread throughout the stratosphere. In the surrounding region, the ancient ocean briefly vaporized, exposing the seafloor before surging back in chaotic motion. One of the most astonishing aspects was the speed of the entire process. From the moment of impact to the initial stabilization of the crater took only minutes. Yet its consequences would endure for thousands of years. When scientists examined rock layers at the geological boundary, they found minerals deformed by extreme pressure, such as shocked quartz, direct evidence of the immense energy released by the collision. These traces serve as the physical signature of a cosmic explosion carved into the planet's crust. The shock wave raced outward at supersonic speed, compressing air and ground like an immense pressure storm. Thousands of kilometers away, the sky still glowed like sunset, even though the sun had not set. The atmosphere trembled, and the ground experienced vibrations comparable to the most powerful earthquakes ever recorded. We will follow how the energy from the impact propagated through the oceans and atmosphere, generating tsunamis and firestorms on a global scale. Phenomena that transformed Earth into a world of chaos within mere hours. The sky was no longer the familiar blue, but a murky shade of red-orange. The ocean before it suddenly withdrew, exposing the seafloor like a vast open wound. Modern geophysical models indicate that the tsunami generated immediately after the Chicxulub impact may have reached heights of hundreds of meters as it spread outward, and near the source may have exceeded 1 kilometer. The energy transferred into the ocean was equivalent to millions of major earthquakes occurring at once, driving water at speeds of hundreds of kilometers per hour. When these waves struck land, they were not merely water. They carried mud, rock, sediment, and even molten fragments of Earth's crust. Geological evidence today reveals chaotic, overturned sediment layers stretching from North America to Europe, proof that the tsunami traveled on a global scale. In many regions, seawater surged tens to hundreds of kilometers inland, sweeping away entire coastal ecosystems within hours. Yet the catastrophe did not stop at the oceans. When the asteroid struck, trillions of tons of rock were blasted into space. Some of this material escaped the atmosphere briefly, entering short-lived orbits around the planet before falling back to Earth. Scientists refer to these particles as tektites and spherules, droplets of molten rock that solidified in midair. Imagine a vast forest once filled with the sound of insects and the footsteps of dinosaurs, now erupting into flames almost simultaneously. Smoke from massive fires mixed with dust and water vapor in the atmosphere. Darkening the sky, sunlight filtered through a dense veil, creating the appearance of a prolonged twilight that lasted for days. Remarkably, the energy of the tsunami did not only devastate the surface, but also disrupted deep marine ecosystems. For marine life, it was an environmental shock that occurred almost instantly. On land, the rain of fire continued for hours. Surface-dwelling organisms had virtually nowhere to hide. Even regions thousands of kilometers from the impact site endured intense thermal radiation and widespread fires. Climate models suggest that the total thermal energy released during this phase may have been sufficient to burn a substantial portion of the planet's biomass. The immense heat, dust, and atmospheric gases would soon push Earth into an unprecedented extreme condition, where temperatures spiked, land trembled, and life faced its most brutal survival test yet. Earth entered an extreme state in which the energy from the impact continued to be released, spreading through the atmosphere, the oceans, and the crust itself. In many regions near the epicenter, thermal models suggest that temperatures may have exceeded 1,000 degrees Celsius for short periods. The air became dry and scorching, thick with ash and superheated gases, creating an environment in which breathing was nearly impossible. But the heat did not come from the surface alone. The immense shock waves generated by the impact continued to ripple through the atmosphere like invisible rings. Tectonic plates trembled. Fault lines activated simultaneously across vast regions, triggering earthquakes on a global scale. These tremors did more than crack the surface. They unleashed massive landslides and reshaped terrain within remarkably short periods of time. Notably, some regions may have experienced pulses of extreme heat alternating with brief intervals of cooling, creating an exceptionally unstable environment. For living organisms, such rapid fluctuations would have been a profound physiological shock, drastically reducing the chances of survival. The oceans were not spared from the thermal upheaval. Seawater near the impact zone was superheated, generating powerful convection currents and altering surface temperatures across vast areas. The atmosphere became a turbulent system where heat and pressure fluctuated relentlessly. Imagine standing on ground that trembles faintly beneath your feet, breathing air as hot as the blast from a furnace, while the sky vibrates under waves of invisible pressure. Food chains began to collapse at their most fragile links, as plants and small organisms could not adapt to the new conditions. Could life adapt to such rapid change? As the immediate heat from the impact gradually diminished, Earth did not return to normal. Instead, it prepared to enter an even harsher phase, one in which light would fade and temperatures would plunge dramatically. This phenomenon is known as an impact winter. It was not a typical winter lasting a few months, but a period of global cooling that may have endured for years. Average global temperatures are estimated to have dropped by about 10 to 20 degrees Celsius. And across continental interiors, the decline may have been even more severe. The dimmed sunlight meant plants could no longer photosynthesize effectively. As their energy production nearly halted, the very foundation of the food chain began to collapse. Herbivores lost their food supply, and soon after, predators found themselves without sustenance as well. Once the first link broke, entire ecosystems gradually fell out of balance. Forests that had once been lush and vibrant became sparse. And in many regions, landscapes transformed into cold, barren terrain. The oceans were not spared. Surface waters cooled in the absence of solar energy, disrupting marine food chains that began with plankton, organisms directly dependent on sunlight. One question arises: why could dust and sulfur alter the climate so dramatically? Fine dust particles reflect sunlight back into space, while sulfur dioxide forms sulfate aerosols capable of cooling the climate by reducing the amount of radiation reaching the surface. This effect is similar to what has occurred after major volcanic eruptions in Earth's history, but on a far greater scale. As a result, the impact was not only prolonged but global in reach. In the extended darkness, the biological rhythms of many species were disrupted. Organisms that relied on day-night cycles for reproduction or migration became disoriented. When environmental change happened too rapidly, the adaptive capacity of many species simply could not keep pace. Notably, this phase lacked the dramatic violence of the earlier hours. Instead, it was marked by a slow but relentless decline in life-sustaining energy. It was this prolonged scarcity that imposed the greatest survival pressure on life on Earth. Geological evidence indicates that this dark and cold interval lasted long enough to produce profound ecological shifts. Many ecosystems had collapsed, and biodiversity had declined sharply. The planet entered an entirely new state, a post-catastrophe world. This was the moment when the history of life reached a great turning point. The moment the dinosaurs disappeared. As sunlight faded and food became scarce, ecosystems began to collapse piece by piece. Large herbivores required enormous quantities of vegetation each day to survive. But as plant life declined dramatically, their energy supply was no longer sufficient to sustain their massive bodies. When prey vanished, the apex predators at the top of the food chain could not endure either. It was an unavoidable biological chain reaction. Once the foundation of the ecosystem was shattered, every level above it fell in turn. This extinction process unfolded over thousands to tens of thousands of years. One of the clearest pieces of evidence comes from the Hell Creek Formation, a famous fossil site in North America. There, sediment layers record a distinct boundary between the era when dinosaurs still roamed and the time after they disappeared. Within the thin rock layer marking this boundary, scientists discovered unusually high concentrations of iridium, an element rare in Earth's crust but common in meteorites. Fossils also reveal an abrupt shift in biological communities. Species that had once been widespread vanished entirely, while smaller, more adaptable organisms became increasingly common in the layers above. Biological networks were dismantled and then rebuilt in a fundamentally different configuration. Smaller creatures with lower energy demands and flexible diets had a greater chance of survival. This helps explain why many small mammals, birds, and insects endured beyond the event. The disappearance of the dinosaurs was not simply the end of a group of organisms. It marked the end of an entire era dominated by giant reptiles. One of the most critical factors was the massive volcanic activity at the Deccan Traps, one of the largest basalt provinces on the planet. The total volume of lava is estimated to have exceeded 1 million cubic kilometers, enough to cover an area comparable to multiple nations combined. These eruptions did not occur in a single day or even a single year. They continued for hundreds of thousands of years, releasing enormous quantities of gas into the atmosphere. Among the most significant were carbon dioxide and sulfur dioxide. Carbon dioxide is a greenhouse gas capable of trapping heat in the atmosphere. When concentrations rise, global temperatures can increase dramatically. Geochemical studies suggest that by the late Cretaceous, atmospheric carbon dioxide levels may have been several times higher than pre-industrial levels today. This contributed to a warmer climate, heated oceans, and shifting sea levels. Ecosystems were forced to adapt continuously to a changing environment. But the story does not end there. Sulfur dioxide, when injected into the atmosphere, can form sulfate aerosols that reflect sunlight, producing temporary cooling effects. This means the climate was not only warming, but also oscillating between hotter and cooler phases over extended periods. Evidence of these fluctuations is preserved in ocean sediment cores and volcanic rock layers, where scientists measure shifts in carbon isotopes and chemical elements over time. These data reveal that the climate underwent multiple significant changes even before the extinction event occurred. Many modern studies suggest that volcanic activity alone may not have been sufficient to trigger a global collapse, but it likely made ecosystems more fragile. It was the small, flexible organisms, less dependent on vast energy resources, that had the greatest chance of enduring this turbulent era. So how did they survive in a world that had just undergone such extreme climatic upheaval? The first creatures to endure were small mammals. They were not large or dominant animals. but weighed only a few dozen grams to a few kilograms, comparable to a modern mouse or small weasel. Their small size meant lower energy requirements, a crucial advantage in a world where food had become scarce. Fossil evidence suggests that many of these species lived in burrows, allowing them to avoid extreme temperatures and thermal radiation after the catastrophe. Deep underground tunnels functioned like natural bunkers, maintaining more stable conditions than the devastated surface above. An omnivorous diet proved to be another decisive advantage. Rather than relying solely on fresh vegetation, these animals could consume seeds, carrion, insects, or whatever organic material remained. This flexibility enabled them to survive a period when most larger species could not. Alongside mammals, another group endured: birds, the direct descendants of feathered dinosaurs. However, not all bird species survived. Fossil studies indicate that smaller, ground-dwelling birds that fed on seeds had higher survival rates. Seeds could persist in the soil for extended periods, becoming one of the few stable food sources during the prolonged darkness. This helps explain why modern bird lineages trace back to those resilient survivors of the catastrophe. Insects proved to be among the most resilient survivors. The fossil record shows that their extinction rate was far lower than that of vertebrates. As forests were destroyed, decomposer insects played a critical role in recycling nutrients, preventing biological cycles from collapsing entirely. Climate and geological models further suggest that environmental changes associated with the Deccan traps may have already imposed ecological stress, ensuring that only the most adaptable species could survive the final crisis. From the ashes of catastrophe, a new era quietly began to take shape. As the last layers of dust slowly settled and sunlight began to return to the planet's surface, Earth was no longer a world ruled by giants. In the first hundreds of thousands of years after the catastrophe, the planet resembled a vast biological laboratory. Ecosystems slowly reorganized. Forests began to regrow from pioneer species, such as ferns and flowering plants. As vegetation recovered, it laid the foundation for new food chains. life returned, but in a structure entirely different from before. With giant reptiles no longer dominating the land, mammals began to expand their ecological reach. Before the catastrophe, they had occupied only minor roles within ecosystems. But as ecological niches were left vacant, adaptive evolution accelerated. Within roughly 10 million years after the extinction event, the size and diversity of mammals increased dramatically, evolving from small creatures into herbivores, carnivores, and arboreal species in a wide range of forms. Geological studies at the Chicxulub crater indicate that ecosystems required approximately 30,000 years to begin local recovery and millions of years to regain high levels of biodiversity. These numbers remind us that evolution is a slow but persistent process, driven by both survival and opportunity. Over tens of millions of years, continents continued to drift, climates shifted, and ice ages emerged. Within that shifting world, primates gradually evolved into forms capable of walking upright and using tools. Eventually, around 300,000 years ago, a new species appeared in Africa. Modern humans. Our emergence is the ultimate outcome of an evolutionary chain of events that began with that ancient catastrophe. If a similar event were to occur in the future, would life once again write a new chapter? Or would we be the first witnesses to fully understand those laws and find a way to protect our planet? The Chicxulub impact event 66 million years ago was not merely an asteroid catastrophe. It was a violent convergence between cosmic dynamics and the biological evolution of Earth. Such rare events become the pivotal knots that reshape the entire history of a planet, turning the end of one lineage into the beginning of a new era. The story of the dinosaurs' final day, therefore, is not only a memory of a distant past, but a sobering reminder of the fragility of our present environment in the face of the universe's unforgiving laws. The history of life is written by events that are random yet decisive. And it is through a deep understanding of these earlier chapters that we gain the ability to consciously shape the next act of our own future within the vast expanse of space. Thank you for staying with WUFO Space until the very end of this journey through the vast universe. If you found this video interesting and insightful, don't forget to like, share, and subscribe to WUFO Space so you won't miss our next cosmic adventures. Your support means the world to us and fuels our passion to keep exploring the wonders beyond.